Up to now, we have looked into non-isolated converters, the buck, the boost, and the buck boost. That naturally leads to the question, what is isolation all about? To understand the needs for isolation, we need to bring the end user into the picture. The end user, drawn here in orange, typically can touch a product physically. Now, if the power electronics inside that product would, for example, be a buck converter, driven directly by the rectified AC mains, represented by line 1, the neutral connection, and protection earth, which is connected to the housing, indicated by the gray frame around the buck converter here, the user might be able to touch the load of the buck converter. Could, for example, be a hand mixer or any kitchen appliance in that case. Now, let's assume we have a failure in the buck converter. For example, the switch, the MOSFET up here, is failing and it is failing to be a short. That would mean that we could have one of the failure scenarios that we have the current provided by the AC mains now running through the body of our end user, the end user standing on Mother Earth, which is the same as the protection Earth signal, and therefore closing the circuit all the way back to the source. And the end user would take all the electrical energy, which could finally lead to the failure of the end user. And that is definitely not acceptable. And therefore, we engineers are required to use galvanic isolation in some of the converters for safety reasons to protect the end user of the product. The main way of realizing isolation in a power supply is through a magnetic transformer. So you have some windings on the primary side and you have some windings on the secondary side. Here indicated by a few number of turns, 1, 2, 3, 4 turns. So the term windings refers to a connection of several turns. With respect to power electronics and safety, creepage and clearance distance are some terms that refer to how safe that transformer would make the power supply. Both of those terms are referring to the direct distance between primary and secondary side and the distance along a surface to reach the secondary side. The creepage is the one along the surface, and the clearance is the physical distance from primary to secondary. Now, the creepage along the surface is very relevant as humidity has quite some influence on the isolation performance of a transformer. And it's not necessarily always the direct distance that's the shortest way to make a short or transfer energy, but it might be over a wet surface. So if you have a PCB that is exposed to a high humidity, you might actually get the electrons to make a connection through the surface, which might be longer than the direct distance between primary and secondary. Practically, there are rules for the minimum breakdown voltage as well, which is somewhere in the 234 kilovolt range. And then a magnetic transformer also has the advantage that there is no direct DC energy transfer, which would be cut off by the isolation barrier in between here. Physically, you turn voltages and currents into a magnetic field stored in the transformer core or in the air if you have an air core, and then back to the electrical signals, voltage and current. Previously, when investigating inductors, we concluded that the current in an inductor cannot change instantaneously. Now that we have two windings around a magnetic path, the current in each of them can abruptly stop or jump, but what cannot jump here is the magnetical flux phi in the magnetical field connecting them. Furthermore, all the magnetic flux that is connecting all the windings has the same voltage per turn for all the windings. Furthermore, Ampere's law connects the number of turns to the currents in these respective windings. So N1 times I1 plus N2 times I2, the current in the winding number 2, plus N3, the number of turns on the third winding here, times the current through that third winding, has to be equal to the externally applied magnetic flux, for example, from a permanent magnet, or just simply equal to zero if there is no AC voltage generating an external flux or no permanent magnet present. Note that the sign of the current here is dependent on whether we have the current flowing into the start of a winding or if it's flowing into the end of a winding. You can freely define the start of a winding through the first winding that you choose, but all the others are either the same way wound around or the other way around, and therefore you need to use a minus sign if they are wound the other way around. The magnetic field lines from the magnetic field H. Isolation by a magnetic transformer is by far the most used technology for creating the safety barrier. But there are also other ways. Optocouplers, which play a great role in the feedback loops around electrical circuits or around power supplies. So you have the power path going in one direction where you transfer the energy, and then you have the feedback path to actually measure at the output and feed it back to the controllers, which might be on the primary side. And therefore, the feedback path also needs to cross the safety barrier. And that can be done optically as there is not much energy involved there. So you can transfer the signal from electrical energy, for example, measuring through a current, an LED, have an optotransistor, so the light in between, and on the base of the receiving bipolar transistor through an optotransistor, it's controlled by the photon sent out from the other side and turns back into a current on the other side of the isolation barrier. Whenever you try to use power electronics inside another external magnetic field, which might be coming from the application, you can use piezotransformers instead of magnetic transformers, which would not get disturbed by the magnetic field. They turn the energy from electric into vibration, mechanical energy, and back again in electrical energy. Seen from an electrical perspective, those devices are like capacitors with more than two plates. They can have isolation voltages up to several kilovolts, but their power usage is typically limited to about 50 watts.